Welcome to this course on probability and statistics. This is an introductory course, or you can say a first course on the probability and statistics, and it is quite useful for all branches of science and engineering. So, to begin with, we introduce algebra of sets. This is required because the modern theory of probability is based on the set theory. So, here we introduce certain elementary concepts of sets, which will be directly used in our definition and concepts of probability. So, to begin with, we start the discussion on what is set, classes and collections. So, we have start with a universal set, let us call it omega, and then we also have the usual notation for the empty set as phi. We call a set of sets to be the class and a set of classes to be a collection. As an example, consider suppose omega is the real line R, and we consider the collection of intervals starting from a to b, where b is greater than a for every real number a. Then this C A is a class of sets for each a, and then if we collect all these classes C A into a set called script E, then this is a collection. For any two sets A and B, which are subsets of omega, let us consider the relation A related to B if A is a subset of B. Then the relation R is reflexive and transitive. It is symmetric when omega is equal to phi. We introduce some further conventions and notations. If the index set I is empty, we make the convention that union of EI's is empty, and also intersection of EI's is the full set omega. The second of this convention looks to be rather surprising. However, it is motivated by the fact that if we take more and more sets in an intersection, then it becomes smaller. For example, if I have two index sets I 1 and I 2, such that I 1 is a subset of I 2, then intersection of E I, where I belongs to I 1, contains intersection of E I, where I belongs to I 2, primarily because the more sets means the intersection becomes smaller. Hence, the smallest possible index set, that is phi, should lead to the largest intersection, that is omega. This convention is also consistent with De Morgan's laws. For example, if I write union of E I belongs to I, complement is equal to intersection E I complement I belonging to I. Let us take I to be phi, then the left hand side is equal to phi complement is equal to x. This indicates that we should take intersection of E I when I is an empty index set, then this should be equal to the full space omega. Let us introduce the concept of indicator function or characteristic function. The characteristic function of a set E is defined to be 1 if x belongs to E, and it is 0 if x does not belong to E. Alternatively, we can write the set E as the set of all those points for which x chi E x is equal to 1. Clearly, indicator function of the empty set is always 0, and the indicator function of the whole space is always 1. There are certain exercises here. For example, if a set A is a subset of B, then the indicator function of A is always less than or equal to the indicator function of B. Conversely, if the indicator function of the set A is always less than or equal to the indicator function of B, then A is a subset of B. A simple proof of this is that if we consider chi A x, then it is equal to 1 for all x belonging to A. And since A is a subset of B, this implies that chi B x is also 1 for these points. Now, for the points where chi A x is equal to 0, include certain points where chi B x may be 1, and for all other points chi B x will also be 0. Therefore, chi A x is always less than or equal to chi B x. We have certain elementary properties of the characteristic functions. For example, characteristic function of an intersection is equal to the product of the characteristic functions of the two sets. It is also equal to the minimum of the indicator function values for those two sets. The proof can be simply obtained by definition. For example, chi of E intersection f x is equal to 1 if x belongs to both E and f and 0 otherwise. That means it is going to be equal to 1 only if chi E x and chi f x both are 1, and in every other case it is going to be 0. So, that means it is equal to the product. In a similar way, the minimum of chi E x and chi f x is going to be 1 only if both chi E and chi f x are 1. That means chi E intersection f x is equal to 1. Similarly, the indicator function relations for the unions, complementations and differences are also there. For example, chi of E union f x is equal to chi E x plus chi f x minus chi of E intersection f x. It is also alternatively equal to the maximum of chi E x and chi of f of x. Once again, to look at the proof of this, we can see that if we write maximum of chi E x and chi f x to be say 0, then both of chi E x and chi f x must be 0. Hence, chi of E union f x will be equal to 0. If maximum value is 1, then either 1 or both of chi E and chi f must be 1, and so chi of E union f will also be 1. The other properties of chi function, for example, chi of E complement is equal to 1 minus chi E, chi of E minus f is equal to chi of E intersection f complement x, which is chi of E into chi of f complement from the property 2, and chi of f complement from the above property is equal to 1 minus chi f x. So, these are some of the useful relationships for the indicator function. We have all heard about the limit of sequence of numbers. For example, you easily understand that limit of a n is equal to a if for every epsilon greater than 0 there exists capital N such that modulus of a n minus a becomes less than epsilon whenever n is greater than or equal to capital N. This shows that the sequence a n is closer to the number a, the values of the sequence a n become closer to the number a as n becomes large. However, the similar concept is not available for the sequence of sets. Here we define it in a slightly different fashion. So, in order to introduce the concept, we introduce the concept of